I'm really trying to trademark the term nanopanning.
Oh, I'm dead. Oh my God, I love that. Hi, fellow geochemists and geochemistry enthusiasts. Welcome to Geochemist Tea, the only podcast for people who love geochemistry with a side of tea. Our mission is to inspire and to shed light on the topics that are not fancy enough to talk about at a conference, but are important to delve into. I'm your host, Sam Schur, and this week we were talking with Aaron Goodman about critical metals, dredged material, and acid mine drainage. Aaron Goodman is a PhD student at the Colorado School of Mines. Aaron, welcome to Geochemist Tea.
Hi, Sam. Thanks for having me on.
It's a pleasure. Aaron, you started off with a degree in chemistry and environmental geology and then worked your way through various labs doing environmental work before making the decision to pursue a multifaceted doctorate at Colorado School of Mines. What more can you tell us about your career until now? For example, how you picked your school, your advisor and degree level, and where you think your current studies are leading you.
From a very young age, I knew I wanted to study something related to geoscience. My family used to take these big road trips around the West, and we used to visit national parks and go hiking and camping and everything. And I just loved seeing all the rock outcroppings, essentially, like just looking at
Really quick
all of what
question then. So were you born? Because growing up East Coast, Long Island, New York, I mean, we did not.
we had an RV. So I actually grew up in New Jersey,
Whoa,
but my dad's a
Jersey.
teacher, and so he would get all summer off. And so we would take these like month plus long trips where we would just go to Wyoming, Colorado, Utah, and
Cool.
just see the West, which was honestly the best part of my childhood. It was amazing.
That's
But yeah, so that's for sure why I knew I wanted to study something regarding geoscience. And then in high school and undergrad, I studied chemistry. I loved chemistry and started to realize towards the end of undergrad, oh, not that many like geoscientists are really that into advanced chemistry. So maybe I can be good at chemistry and study geoscience. And then that naturally led me to geochemistry. It was actually kind of funny in terms of finding a school to do a PhD. My parents were actually on a road trip around the West, and they drove through Golden, Colorado, and they mailed me a t-shirt from the School of Mines and said, "Hey, you should check this place out." And so I went on Google and I looked up the professors there and the programs and was, oh, hey, this actually seems like it would be a really good fit. And then basically asking professors what kind of funding opportunities do you have and what kind of research would I be involved in and how are you looking to take on new students. And my advisor Jim Ranville said, sure, come on down. And so here I am, and it was a really great decision. Mines is an amazing place to get a PhD.
I think that's so interesting, the way that you were so proactive in really trying to find out what it is you want to do. Because I've talked with a lot of people that are still in their undergrad, and there's just all this, just, I don't know what I want to do. Well, maybe they do know what they want to do, but they don't know actually how to pursue it. And it's just these light feelers out there when really I think what you're saying and part of your story is that it was this very proactive approach towards being like, okay, these are my interests. How do I get to where I am? And yeah, it was maybe a little bit serendipity that your parents sent you that t-shirt, but there was a lot of, in essence, research involved in finding out how to go about doing your PhD and everything. And I think that's a pretty interesting story that you just shared with people out there that are looking post undergrad. What's my next step?
Yeah, I guess I skipped over all the indecision
I
because
love that.
I surely did. Like senior year of college, I did cast around for some jobs and was like, oh God, none of these, I'm not qualified or they're just not interesting. And so I guess I just have to go to school. And then I was like, okay, I'm not interested in joining the workforce right now. So a PhD sounds great. Like my grades are good. I'm interested in research. I've done a bit of research in undergrad. So it was a little bit more tentative of let's just try this thing out. And then as soon as I got here, it was like, oh man, this is like the environment I was meant to be in. And I definitely, it's convinced me to stay in academia, or at least that's my plan right now.
I think that's really cool that now that maybe I teased it out of you a little bit because so then all right. So to the crew that's listening out here, I guess my own story was I had when I was graduating, I wasn't from my undergrad, I wasn't sure if I wanted to be a professor. I know that sounds, oh, no big deal. Say I wanted to be a professor, but I thought that I really wanted to do research. So for me, I never wanted to just directly join the workforce. I wanted to try something out, but I knew also for me that it was a big commitment just to jump right into a PhD. So for me, I said, okay, let's try out a master's. Let's see how it goes. I love my master's. It was great. Except what I realized there, because I spent a lot of time in the field with my professor and with other research assistants, and then another professor from a different university, I realized what it went into it. I went to university in Canada. And so for that, you have the NSERC grants, this, that, tons of different funding. And I realized how much more there was to it and how much politics there was in being in academia. And between that and then just while you're doing your research, some of it's great, some of it you get a little bit sidetracked and you get a little bit like, oh my God, I'm in the deep end here. How do I figure this? How do I come to the
Yeah.
surface? So I realized from that experience that while what I had done was pretty incredible work, and I attribute that to my supervisor, Willie Williams Jones, it just wasn't something that I was interested in pursuing even past a master's. So for me at that point, I think what was really open to me was probably more the mining stream, because a lot of people in my lab group my lab group was, even though it was geochemistry, was also economic geology. And so I tried out, I guess for the second time, because I did one job in undergrad of doing just soil sampling. I tried it out again and I ended up really loving, it was in the middle of BC somewhere. It was beautiful. It was a great summer.
Nice.
I tried it out
Nice.
again and I was like, oh my God, this is amazing. And then, of course, I had graduated in another big bust in the industry. But that had led me to Chile, to all these other places. And now here I am in the mining capital of the world, Washington, D.C., just living the big life. That's a great story. And I appreciate you also sharing your indecision, because I think that when people that are listening or students see different people that have had what seems to be a lot of success in their careers at different shows, whether, we were just at SEG, they have a big mentoring program, and it seems like a very linear path to success. And I just think that everybody should always know that the path isn't linear. I don't know if that's unique
Oh
to our
yeah.
industry, but it's very true. So,
Yeah, definitely. I mean, there's always room in life to learn more, no matter where you're at. You can always go back to school. You can always go pick a different field. As long as you're qualified, you can do whatever you want.
yeah, and I think that the fact that you really love chemistry and you had such a fundamental foundation for which then you built on, but then building on other ideas that you had of going into the geosciences, I think that's an interesting path too. Because I've met a few different people that have been in engineering or had, similar backgrounds to yourself that are just, how do I get into it? Is, well, you have a fundamental basis that many people don't have. And actually, that's
Mm.
pretty attractive, because I think while geology itself is a very special science, but having these fundamentals, whether it's in physics, whether it's in maths, or it's in chemistry, there's so much potential for you then to develop a very different kind of career in the geosciences that maybe if we just do geology degrees, we don't have access to. My last question here, and I think we got there already, but do you have any advice to our listeners that want to pursue geochemistry in the way in which that you have?
Well, I'm only 26, so I don't have a wide world of knowledge to share with people. But I don't know. I mean, I think I mean, if you're an undergrad, just getting involved in research as soon as you can, and just don't think that you're not good enough. There were a few opportunities that I had in undergrad to join a lab a bit earlier than I did. And I was like, oh, I don't know if I can. I don't know how confident I am in this field or whatever. And it's like, just do it. You're never going to feel like you know what you're doing right away, right? You're always going to get in the lab for the first time and be like, oh God, what am I doing? So just get that out of the way early and then start building your confidence as soon as you can.
And I would add on to that in saying that many job descriptions out there, whether you're talking more the academic side, but in the sense that if you're trying to apply to something in industry, whether it's environmental, whether it's mining, whether it's oil and gas, what you see in the job description is a wish list. A lot of times that person
Mhm.
doesn't actually exist, but it's a
Right.
wish list. So even if you don't have 10 years experience, you can't speak 5 languages, you don't have a background on this, that, and the other thing, just apply. The worst thing could happen is that you don't make it past round one or round two, but it's important that you keep applying. and at the same time building up other skills in different ways so that you can put more on your resume as you go. I think that's really great
Exactly.
advice. Hmm. All right, so now it's that time of day where I'm not sure what Aaron has brought us. He's clearly not as seasoned as some of our others out there, but a lot happens in university. So I'm wondering, Aaron, what kind of tea that you've brought us, and really honestly, it's just time to spill it.
All right. Well, the tea is it's not really that hot of a take. I work, a lot on environmental chemistry and situations that arise from that area. And my tea is that if you're a mining company, it is actually beneficial for you to really invest in that side of your operations and environmental, not just because, oh, we want to look good, oh, we want to show people what a good job we're doing with the environment, but actually because you could recover real value from both your waste, and we'll talk about that a little bit more directly, but then more broadly, just investing in technologies that the environmental side of science is bringing. And there's a whole nother side of my research that we're not going to talk about at all, but these new emerging techniques in environmental geochemistry, environmental science that actually could really benefit the mining industry. And so basically, yeah, I guess that's kind of a rambling way of saying the T is that don't just say that you care about the environment. If you actually invest in your environmental side of your company, of your mining company, you might actually come out ahead because of it.
And do you have somewhere to direct people to look at the other side of your research? Do you have any papers out, anything coming out?
Yeah, we have one paper out. Well, the what I'm just alluding to is, and again, we can just kind of say this is a minute of totally irrelevant to the rest of the episode because it's a completely different side of my
It's
research.
really fine.
But basically, people developed this technique called single particle ICP-MS, where you look at nanoparticles with a mass spectrometer in an aqueous suspension. And it was developed pretty much primarily for environmental studies, looking at nanoparticle release from human activities, looking at nanomaterials in food, looking at nanomaterials in agriculture, and all these sorts of environmental things. But we're actually trying to use it to explore for ore deposits and looking for nanoparticles of gold and pathfinders and minerals and things like that in stream sediments, soils, etc. And we might be finding out that we can. So stay tuned. We've got one paper out that's a proof of concept. We're working on a whole bunch of other stuff in that area. And maybe in the year, I'll come back on the podcast and talk about
I
all
love
that.
it. I was gonna Yeah, we talked about with Duncan McLeish a little bit about his work
Hmm.
in Bruchac, where he's
Yep.
talking quite a bit about nanoparticles. I myself am no stranger to them either, with some of the work that I did and some other people. Well, Duncan is actually part of my old lab group. So, yes, would love to talk more about this. We'll have a to be continued, and you'll have to bring some
Hmm.
other tea to dish. So, make sure that you do something a little bit
Yes.
crazy over the next year so that it can just be bit more of a crazy tea. But I like this though. I think that it's really relevant to there are projects out there where people are working on how better to remediate their projects in a way where they don't lose money, but at the same time, I think that your point of starting earlier in the process is something that is really interesting for new mines that are currently being opened or things that are well before the stage in which they have to start thinking about remediation. And I think people are starting to think about remediation even earlier in the process now, but I think any
Right.
kind of new tech coming out, right, is more than welcomed for the people of this little podcast to hear about. So cool.
Right.
We will chat with you in 12 to 18 months about this. All right. So then now to start our conversation on critical metals and really focusing a lot on the two papers that you brought to us. Could you talk here about our overarching theme, namely critical metals, and how the papers that you brought to us and your research tie into it?
Yeah, so critical metals are defined, well, they're defined strangely because some people call them critical metals. Some people call them critical minerals, which is a bit of a sticking point for a lot of geologists and geochemists because the list of critical minerals includes almost zero minerals. It's like I forget which there's two minerals on there and then 50 elements, but they just refer to them all as minerals. So it can be really annoying. Oh,
Yeah.
critical minerals, lithium. Well, no, lithium's not a mineral, but
Mm-mm.
that's okay. Um, I say critical metals. Some people say critical elements. It just varies, but it doesn't matter what you call them. They're just broadly defined as elements that are essential to advanced technologies, particularly looking at the energy transition, so renewables, and particularly they are or their supply chains are at risk of being disrupted due to geopolitical factors. So there's two sides of it, right? How do we use them? What are they used for? And how easily do we have a domestic supply? And how stable is our international supply of those metals? So those two factors kind of come together to define what a critical metal or a critical mineral is.
Yeah, and I something
Um,
that always bothers me, and I'm not sure that we're talking about this because I think it's maybe a little off topic, but something that really bothers me is that about this whole situation of critical minerals, metals, elements, whatever you want to call them, but we'll call them metals because that's what you want to call them, is that, for quite a number of them, it's not the fact that we don't have them in supply. It's just that we have no method for which to extract them. So it's like, what are we even
correct.
talking about here?
Correct. Yeah, yeah. And we'll definitely, I think we're going to be able to touch on that a little bit
Love that.
later. But yeah, so in terms of which ones we're looking at with these two papers, the one paper on the acid mine drainage is primarily focused on rare earth elements, the lanthanides, rare earth elements, whatever you want to call them. I think all of them are on the list of critical minerals, but there's a few that we really need. We definitely need some more than others. Neodymium and praseodymium in particular are used in alloys to make permanent magnets, and those go in wind turbines. So that's really useful for transitioning our energy sources. If we want to put up wind turbines, we need these magnets. And so those are probably the biggest ones that you'll hear about in the sense of being really critical. And then for the dredge material, we were also seeing high concentrations of rare earth elements. So we investigated the geochemistry there. But we also saw elevated cobalt and nickel, and those are also critical, and they are used in battery technologies and things like that.
Neat. And so for anybody, I forgot to mention them until now, but the two articles that we read for this week, which are also on the website, geochemistry.com, are Rare Earth Element Recovery in Hard Rock Acid Mine Drainage and Mine Waste, a case study in Idaho Springs, Colorado, and also Critical Metal Geochemistry in Groundwaters Influenced by Dredge Material.
Yep, those are the two studies, and they're looking at two cases where we have these acidic, aqueous potential sources of critical metals, right? So we're looking at something that we can remediate and also possibly recover metals. Not from these two examples alone, but using them as case studies for the broader sense nationwide, we could use these types of secondary sources to increase our domestic supply of these metals while also remediating, in the case of acid mine drainage, remediating existing environmental hazards.
I love that. That's really cool. So I love to start out our Q&A with some softball questions. Critical metals, which ones are we going to talk about today? Are there any things that we shouldn't be focusing on so much? Just let us know, have we missed any right now?
Well, I can just pull up the list of critical minerals and we can look at the fact that pretty much the whole darn periodic table's on there.
Yeah, I've seen
But
that.
I mean, so the rare earth elements are 14 of them. So that kind of checks off a lot of them. And then cobalt and nickel were the other two. So it's kind of like, there were other, like in the dredge material paper, we did talk about manganese because it is on the list. And it's like cool to say, okay, this is another critical metal that has high concentrations that we could potentially recover. But it's mostly about, you have to go one layer deeper and be like, okay, what grades are we talking about for something that we're actually going to produce? And how does that actually compare to the grade that you would produce from a mine? And when it comes to some of these, like the concentrations are just low enough, even in the acid mine drainage, like zinc is a critical metal, right? Even if we have ppm levels of zinc in water, if you tried to recover that, you're not going to get anywhere close to anything economic. But when it comes to things like neodymium, all of a sudden that becomes much, much easier because both of the differences in how they're mined in the traditional hard rock mining sense and how critical they really are. Like how badly do we really want them? So there's a lot of factors that influence what elements we talk about, but the rare earth elements, cobalt and nickel, were the ones that, based on the concentrations that we had in the sources, plus how critical they really are, plus the sort of possibility or feasibility of actual recovery in the economic sense, those factors combined to guide our selection and what we were looking at.
I find the cobalt one pretty interesting. Obviously, most of our cobalt now comes from the DRC. And so you're saying that potentially we have enough domestically in some of this acid mine drainage where we can do something of value with it.
Yeah, have to just, the disclaimer with all of this is that we're talking about supplementing our
Yeah.
sources. We're not
Okay.
talking about replacing our sources. There's obviously a whole host of issues that come with mining these metals a lot, especially the rare earths and cobalt. And we're not really saying that we're going to solve all those problems. But what we are saying is let's get something of value out of these sources and offset treatment costs and whatever else, right?
I love that point, and I think it's a really good one. All right, so then let's pivot from talking some of the softball stuff that we addressed for the last 5, 10 minutes. And let's talk about this dredge material with the critical metals that you've been studying. According to the research, there's sulfate making bacteria that is generating pyrite at the bottom of a canal in the Chesapeake watershed. Could you expand on this and its importance as a potential critical metal resource?
Yeah, definitely. So this,
So
I'll just say
interesting.
that this is, yeah, this is one of the those things that's like really fascinating and really interesting to be a part of, because for a long time we've known about, let's take the other case of acid mine drainage. We've known that it has high metal loads. We've known that it's acidic, and it makes sense, right? It's coming from mine, it's whatever. We've kind of known that this is a thing for a long time. But what's really exciting is that dredge material is this brand new kind of, I guess, the idea of using the dredge material for something is something that's really emerged in the last, I don't know how long, decade or so. And people have looked at using dredge material for road construction, for other sorts of like engineering type applications, but there's really been no investigation of the actual contents of the dredge material. And to our knowledge, I think this is the first investigation of dredge material with an eye for metal recovery. And one of the reasons that it's so exciting is because the sheer volume of material that's dredged in the United States alone on an annual basis is just like insane. I think about every harbor, every river, all the Great Lakes, all the dredging operations that are taking place nationwide. And so if we can come up with a way to use that as a source of these metals, then that would be incredible. So now I'll answer your question about what's going on here. The area we studied was in the Chesapeake watershed. The Chesapeake and Delaware Canal, or the shipping channel, is what is being dredged that's generating these piles of dredge material. And so there's sulfate in the water, and on the bottom of the canal, our hypothesis, our kind of idea of what's happening is that there's sulfate-reducing bacteria. So they're taking sulfate and they're generating sulfide, and they metabolize sulfur in the same way that we metabolize food and oxygen. And so they're generating sulfide, and it's in the form of hydrogen sulfide. And then essentially it combines with metals that are present in either the water or in the sediments, and it generates sulfides. And we're seeing this mostly with iron and manganese, and we're seeing really nice correlations between sulfur, iron, manganese in our analysis. And that was one of our lines of evidence for the fact that we think that there's sulfides being formed on the bottom of the canal. So then we have this sulfidic material that's being dredged, and it's being pulled up from the bottom where it's anoxic, and it's being brought up to the surface and disposed of on land. And there it comes into contact with oxygen, and it comes into contact with rainwater and groundwater to an extent too. And the sulfides oxidize and generate acidity, and then the metals are released. That's essentially our main story there, that we have this sulfidic material that's being disposed of on land, and the sulfides are oxidizing, and metals are being liberated. And so why that is a good thing is because we're essentially saying we have this large volume of material that the US Army Corps of Engineers needs to do something with. And we essentially can use it as a heap leach and recover things like cobalt, nickel, and rare earths from it. So that's really something that we would love to be able to do with it.
I'm just thinking all about source, and I just find it so interesting. So the dredge material is just sediment coming off from whether it's dams, canals up there, but it's just filling up in the watershed. They're dredging it to make the channel deeper so that ships can
Hmm.
pass through.
Yep.
I'm just wondering, do we just naturally have that much cobalt, nickel coming from, I guess it's just Appalachia up there?
Right. That's one of the things that we need to investigate further. The paper we published was a first pass, just an overview of the geochemistry. And the main things we were trying to figure out was, okay, is this stuff derived? Are these concentrations that we're seeing derived from the dredge material? We're fairly confident we can say, yes, it is coming from the dredge material. We are also fairly confident that it's coming from sulfides in the case of cobalt and nickel. More on the rare earths in a bit because we think something slightly different might be going on there. But like a follow-up study, we're actively trying to get funding to keep studying this. And one of the main questions is, yeah, where are these metals coming from? Is it just the fact that if you have really low, like sub ppb concentrations in any natural water, does the presence of the sulfate reducing bacteria and the hydrogen sulfide that they're generating, is that just a concentrator of all these metals, right? So is it just scavenging these ultra trace amounts from the water, and over time, over the whole year of all that water flowing by, well, maybe actually if you're concentrating the cobalt and nickel from a very large amount of water into a smaller amount of solid, maybe that is why the concentrations are so much higher, and maybe that's why we're seeing the geochemistry that we're seeing.
Yeah, and then to that point, then moving forward from that, we're not talking about just only the dredge material from this one part of the Chesapeake watershed. We're talking about, okay, now as something that we can have as part of our reserves because we have to dredge so much in the US. And I'm sure at other places that have busy seaports. Now it's about, okay, well, we can go around to these different sites, try and remediate them, but understand which ones have, if we're looking for nickel cobalt, for example, testing the different dredge materials around the US and then just being able to take them to a certain place, concentrate them, and doing that on a continual basis as part of the remediation strategy.
Exactly.
Yeah,
Exactly. And that's
very
that's
cool.
one of the things, yeah, that's one of the things we really need to figure out. Is this phenomenon, like, does it span across different environments, or is it really something that's unique to this area?
Mm,
Um, and actually now this is a good time to pivot to the rare earths actually, because
love it.
in this Atlantic coastal plain, that's what the kind of regional geology is. There's a few geologic formations that have the mineral glauconite, and that mineral, it's a mineral that is known to sorb high concentrations of rare earths. And so essentially what we don't really know is, we've talked about the fact that sulfides are oxidizing and they're releasing metals and they're generating acidity. And so one thing that we don't know is, does the dredge material itself contain the rare earth elements, or are the rare earth elements simply being desorbed from the local geology as the acidity is being generated from the dredge material? And that's an important question to answer, because if it is the latter, then we are looking at possibly the rare earth concentrations being more confined to this Atlantic coastal plain system, versus being this universal phenomenon that we're going to see everywhere. But if somehow that's our leading hypothesis, but we can't rule out the fact that they are actually derived from the dredge material.
Yeah, I'm looking at the composition of glauconite right now. So it looks like it's, as you say, it's a mica, and it's just as micas are, just a garbage bag of different elements. Okay. All right. Now you have me thinking about just rocks in general in Appalachia, which I didn't do a lot of studying on, but all right, glauconite. Now we know. Okay.
Yep, it's out there.
It's out there. Oh my. All right. So then now that we're talking about we're talking a little bit about pyrite. Let's move on to our second topic. We've already sprinkled in some acid mine drainage here and there.
Hmm.
But I think something that we learned from an early age about maybe it's just in the American education system, I'm not sure. Or maybe it was just the 90s and the early 2000s where it was very in vogue. But we hear a lot about acid mine drainage. Um, and so nowadays, from the pre feasibility stages, we work really hard for this not to be an issue in our minds. However, there's plenty of examples of acid mine drainage in the US alone. What prompted your lab group to think about acid mine drainage in this way, that it could be a potential resource for critical metals? And also, what environments do we have to focus on? Is it all deposit types, or is it really only specific deposit types for specific critical metals?
Yeah, great questions. To be honest, one of the main things that prompted our lab group to think about this is funding. There was just a lot of calls for proposals on secondary sources of critical metals, critical minerals rather. And being in Colorado, we're right next to the Colorado mineral belt, and obviously Colorado
Yeah.
is one of the big states when it comes to acid mine drainage, just because we have so many old abandoned mine sites that have been in need of remediation. And so it was just a natural progression to say, oh, okay, let's write some proposals and let's get some funding and let's go study this stuff. So it's a good thing that we did, because it happens that the paper we wrote about this, the case study in Idaho Springs, it happens that one of the highest concentrations of rare earths in acid mine drainage that we've seen so far is just 30 minutes up the road from us in Idaho Springs.
Love.
So it really is convenient. I was able to just drive up there. I know all the treatment plant operators super well. Just go in, say hi, grab a couple gallons of water whenever I need it. So pretty nice.
Head to the ski
Um,
slopes for the rest of the morning.
yeah,
Nice.
exactly. Um,
I know what you guys do at
but
mines.
oh yeah, yep. But yeah, and that actually gets to another project that we're working on right now, where we're doing a regional assessment of most of the high volume acid mine drainage sources in Colorado. And the study's still ongoing. We don't have any big conclusions yet. We're not necessarily writing a paper yet, but just from looking at the data, it's not that complicated. If the mine drainage sources that are going through the Leadville limestone before they make it to the treatment plant, they're all buffered by carbonates, and they're coming out of the ground at pH 6.5, pH 7, and there's not really any metals left because they've all already been precipitated by the time they get there, right? So where you have carbonates buffering the mine drainage, that's not really going to be an area to look. The other thing that is not that complicated is, if you want copper in your mine drainage, go to a copper mine. If you want, the things that are in the ore are likely to be in the mine drainage, right? So we've seen where we have abandoned gold mines where the gold is in tellurides. Those are the only mine drainage sources that we see with tellurium in them. And that's an interesting one. We haven't really looked at that much at all, but tellurium is one of those things that if you can recover from acid mine drainage, that would be huge, because it is one of those really critical elements. To bring it back to rare earths, we still don't really know why some mine drainages have high E's and some don't. Um, we have a couple of sources, mine drainage sources in Colorado, that are similar pH. They're draining similar types of ore deposits, and one has really high concentrations of rare earths and one has almost none. And we're really searching for an answer for why that is. So if you have any ideas, hit me up.
I mean, I would just think that it would come down to the initial mineralogy of the deposit. And I know you want to say that, for instance, all porphyries the same, all epithermals, all, but as you come to work in more and study more of them, you realize that while these general models for exploration can apply, they're oftentimes just so complex and so different that you just can't blanket apply things to them. And so when you think
Right.
about whether it's the stocks that aren't ore bearing, or it comes to the ore bearing, I mean, and then it comes to the alteration of the stuff. But
Yeah, that's
yeah,
what I was going to say. Because I mean, if you think about it, the models of the deposits are primarily focused on the ore metals, right? The
mhm,
metals themselves, like copper and gold and silver, lead, zinc, everything. Not as many people are worried about what form the REEs are in these types of deposits. And so now
yeah.
we're just scratching the surface on that. Of course, people have used rare earth patterns for a long time in geochemistry to look at um,
enrichment and stuff.
I guess that's a major question is it related to the ore? Is it related to the alteration? Is it related to the host rock? Why? We know obviously that the major things like pH plays a big part. Like that's pretty easy to figure out. If it's low pH, you're going to have higher metals. But why in some mine drainages do we have high rare earths and some we have very little, with some other variables being held constant? So it's an active area that we're working on right now.
I think it's just an example of one of those where whether you have to go back through the files for any kind of USGS report, if you go into the archives of who used to own it, you'll always find that things haven't been studied as hard as you needed them to have the answer immediately. So you have to do for each study that you're going to do, you're going to have to do quite a heavy study into the background geology and into what intruded what to really understand what those, why you have those different minerals there and what phase they came up in. So yeah, it's not going to be an easy answer, especially I don't want to blame explorationists or anything or mining companies, but a lot of times things can be for various reasons. I keep stopping on this point, but I'm just going to say it. Hey, it's my podcast. I should get a disclaimer on here. But it's just that I've worked on many projects across many regions at this point, and it's very variable how well the geology is understood. There's a lot of dogma involved. There's a lot of inherent bias, especially if people haven't left certain areas. A lot of times you're missing that component of a really good geological fundamental understanding of the area. So I think once you, for the different sites that you select, I think that once you really put in the time to understand the fundamentals of what was there to begin with, what happened next, then you'll start to see why certain sites will have maybe high monzonites or high whatever the other, different types of, titantites, rutiles, etc. So, yeah.
Yeah, definitely.
Oh man, now this just became a session of some kind of, I don't know if it was like me being a counselor upset about the state of geology in general. I'm on some really good projects right now, and I've been really impressed by the way that they're doing their geology. So I think that's given me a lot of hope, but I've seen a lot more bad projects than good projects, and that made me sad. So I am not the answer to everything though. All right. So in your papers, you document a lot of extraction and concentration methodologies, which I think we've touched on a little bit of. But since we are geochemists here, could you dive into it and explain some of these methodologies a bit more and comment on whether at this point these are economically viable?
Yeah, definitely. So basically what we're doing, or what we showed in the paper on the Argo tunnel, that's what the source is called up in Idaho Springs. It's the Argo mill is a famous mill that's connected to this tunnel that basically drains a whole bunch of mine workings in the Black Hawk Central City district of the Colorado Mineral Belt. And so we applied a staged pH adjustment to it. Essentially, we're not really doing anything super fancy. We're essentially just doing a multi-stage precipitation. So first, we take the raw mine water and we raise it to a pH of about 4, and we precipitate out all the iron. And at this stage, none of the REEs, or very few of the REEs, come out with that iron precipitate. One thing that really was cool that we noticed was thorium was coming out with that iron precipitate. So there's wasn't a ton of thorium in the mine drainage in to begin with, and there's certainly nothing to make anybody worried about, like, oh, thorium radioactivity, right? But it was kind of cool that we were able to remove, I think it was like over 99% of it at that stage. And so then you don't have to worry about that like later in the processing of the rare earths and things like that. So the first stage was essentially designed to remove things that are low value like iron and that could potentially be problematic like thorium. And then we take the supernatant water, the clear water without the iron, and we raise the pH again to about 6.5 or 7, and we precipitate out aluminum, which is the main oxyhydroxide forming metal that's coming out at that stage, and it's forming these precipitates, and the rare earths are sorbed to the surface of those aluminum precipitates. And because oxyhydroxides in general, if you learn about their geochemistry, they have high surface area, they're readily sorb trace metals. And so we have this aluminum precipitate that we've digested and measured the concentrations. And it turned out that the total rare earth content was about 0.4% by weight, which is pretty good. We're in the percents, we're not in the ppm world, which is cool. And then this is pivoting towards whether they're economically viable. We're certainly not ready to say that, yes, they're economically viable, send it off to the processing plant. But what we do know is that the sorbed form of these REEs to the aluminum precipitate, it's fairly similar to the ion adsorption type deposits that you see in southern China, the clay deposits, the lateritic clay deposits, and those are really renowned for their processing, right? It's a fairly easy to process them. And the concentration that we're seeing, which was 0.4%, is actually in the range of those ion adsorption type deposits in China. So that's some pretty solid evidence that, maybe, hey, we're not really ready to send it off to the processing plant right now, but we're kind of in the ballpark, both in the geochemical form and the actual or the actual grade of the product that we're producing.
And what was the phase that the re started in?
So they're in the water. Well, we
Oh,
don't
they're in
know in
the
the rock, but
okay.
yeah, but in the water, they're complex with sulfate because there's so
Okay.
much sulfate in acid mine drainage. That's pretty much everything. At least that's what geochemical modeling tells us. We actually were interested in doing some higher level analysis on both the water and the precipitate, like doing some like synchrotron work, some XFs, and actually understanding the true nature of the bonding of the REs, both their state of whatever they're complex with in the water, which again we think is sulfate, and then basically trying to figure out exactly how they're sorbed to the aluminum precipitate. Is it an inner sphere complex, outer sphere complex? There's a whole rabbit hole that we could go into about like how they're actually bound in these.
I love this rabbit hole. If we can do it in under 2 minutes, we can. No, I'm kidding. If you want to go into the rabbit hole, please. This is the safe space for rabbit holes.
I'm not ready. I don't think I'm ready to go into the
Okay, okay, okay.
synchrotron
So
rabbit
this is
hole.
okay. So this is 12 to 18 months. We'll go down the rabbit hole. Okay, fine with. No, that's really neat. And I like how you were able to pull it back to some of the famous Chinese clay deposits. I think that's really interesting, especially as our next question leads into a bit of what goes on in terms of reprocessing right now. Something that's a huge challenge to critical metal potential economies is that currently we have to send everything to China to get processed. All these are these minerals that we talked about just now in a state that is ready to be used. And I think that the answer to that, what we were talking about just now, the ones that are in the waters, is yes. So in this sense that they are that kind of, in quotes, pre-refined. But some of the other stuff that we talked about before with the rees, save for this last little piece, what are the next steps that we need for them, all of them actually, to be market ready? And really, in this sense, too, does this require a huge environmental impact? Because I don't know if probably everybody listening to this podcast is aware of this, but what happens in China is hugely detrimental to their environment, which is kind of why it's happening there.
Right. Yeah. Well, so it sounds nice when I say, oh, the grade is there and the form is there ready to be processed or whatever. We do still have to contend with the fact that all of the lanthanides are occurring together, and that's not useful to anybody until they're separated. So I guess say the first hurdle is processing. That would be the difference between your traditional hard rock like Mountain Pass, California, right? Where they're in bastnasite, which is this mineral that just has all the light REs in it. And that has to be broken down. The REs have to be solubilized, and then they have to be separated. We kind of get to skip a little bit of the first step because they are in these kind of more readily accessible sorbed form onto these precipitates. So that is good. But we still aren't ready to go because they do have to be separated into the individual elements. And this is another area that, this is outside my wheelhouse because it is more in the realm of separation chemistry, right? But I've been at workshops and been on meetings where there's just been a huge focus on how do we make this a multifaceted solution? Like, how do we both mine and produce rare earths domestically, but then also how do we process them domestically? Because even our one mine, Mountain Pass, California, as soon as the ore is mined, it basically goes on a boat and goes over to China to get refined and separated and then comes back here. Well, and often things are manufactured there too. And then it comes back here as the finished product. But I know in that space, I'm not really, again, it's a little bit outside my area, but I do know that there are a lot of efforts to look at securing funding, both in collaboration with the government and private companies, to build rare earth processing facilities domestically. I think there's talk of linking the development of a couple of rare earth mines that we have some rare earth deposits in the United States that we haven't mined. And so I think there's some talk of linking the development of those deposits with the production of rare earth concentrates here in the US. So that's an area for everyone to look at in the next couple of years. Well, more like probably next couple of decades.
Yeah. Oh my goodness. It's just, and maybe now we get into the geopolitical part of this, but the big push is to have everything mined here domestically. And I'm sure this is true of other countries and especially Western countries. But then there's this whole other part where it's just environmentally frowned on and mining is bad, et cetera, et cetera, et cetera. And we leave ourselves open to decades of trying to build a replant.
Yeah,
And we want to be independent, and we have the resources to do it, but we can't do that if everybody's worried about everybody else's feelings. And we're trying so hard, as your research shows, to do it in a sustainable way that's not detrimental to the environment. So,
right. Yeah, and I mean, I think maybe this is just me being super optimistic, but maybe as
mm,
work continues in this area, we can start to tell people like, hey, we are going to mine this area, but we also have a plan to not only manage the waste, but actually keep recovering things that we need out of the waste. And so kind of, I don't know, it's if you're using as much as you possibly can and generating as little waste as you possibly can, then maybe that will translate a little bit into a more positive public sentiment. I don't know. There's so many issues with
there's so many
convincing
issues.
people that mining
Yeah.
is,
I think it's just, I think there's a lot of problems in the education of it. And maybe to continue on our optimism path, I was just at the SEG London
Mm,
conference last week, and in that, maybe to get new geologists, and they're talking about recruiting people. This sounds terrible, but recruiting people for when they're young to get into the
yeah.
field of geology. But maybe that's also something we said that for all of us, when we have the opportunity to be educating people from an early age about how the mining of yesteryear is not so much what we're seeing today, and that we have all these plans, because it's very hard to, we're a nation of 350 million people. The world is 7
Mm,
billion people. How do you convince all these people that we're not necessarily out to get them, but also this is what our future is? Like, we can't
yeah.
not embrace our
Yeah.
future.
Yeah.
So
Well, and it's kind of what our present is too. You
you're
get on
not
your
wrong.
phone or you get in your car, right? Whether you know it or not, you are living in the world of mining. You just don't know it, right? And so I
Yeah.
think that's one of those things that it's hard for people to think about.
Yeah. That, oh, I thought of a literary term, the willing suspension of disbelief, but really it's more just that denial.
Yeah.
So for our last question here, for both the dredge material and the acid mine drainage, critical metal recovery, what's your next steps? We talked a little bit about some of them. Curious just because I'm nosy. Any patents coming? What are we thinking?
So, well, one of the nice things about what we're doing with the acid mine drainage is it's so simple. You can't put a patent on raising the pH of water to precipitate things, right?
I love that.
So, one thing that we are doing is we do have a project that actually just got funded from a major mining company to look at one of their high volume waste streams in the US. And so what we're looking at doing is spending a year in the lab tweaking the process that we already have that we developed for the Argo tunnel. And then we're partnering with an engineering firm to actually go to the site and implement a barrel scale pilot test. So that's the kind of thing we're really excited about now, is we're not just making something in a beaker and showing that people, oh, okay, like this, we have this product that we made 10 grams of. Let's actually go and run it at barrel scale and run it for a week and say, okay, we produced this product. It actually worked on this sort of process level. So that's where we're going for the acid mine drainage. I would love to say that we have tons of work planned for the dredge material, but we're really trying to get funding for it. We need funding to basically do a big field campaign and go and actually and just do a ton of sampling and analysis and actually pin down what the sources are of these metals and then try to expand that to other environments. So that's something that we'll hope to do over the next couple of years.
I love that. I love when people's research becomes applied. I see a lot of presentations of research where people have recovered the formation of how a certain ore deposit was made based on 5 samples from one drill hole or something like that. And it's really frustrating. So I love that. I had somebody, oh my God, and this is another one I'm going to get in trouble with. I watched a presentation recently where somebody's research proved that I want to say it was Arizona porphyries were created by flat slab subduction. And I was like, I don't understand why flat slab subduction is mind blowing. We know that is really important for porphyry formation. Like, what did we contribute to science? Anyway, I'm really impressed that you have a contribution here to science and hopefully to, how this mine's going to work and maybe how we're going to look at different commodities in the future. Well, different waste piles in the future as potential commodities while also remediating. I think that's very cool.
Yeah, that's what we're hoping to do.
Cool. So I just want to thank you so much for being here. And I hope that for everybody that's listening, that maybe this sparked somebody out there with some ideas to rethink their own projects or mines, critical metal recovery. And I want to thank everybody for listening to Geochemistry, and maybe this time me going a little bit off the rails. And yeah, big thanks to Aaron Goodman being on the show, dishing some tea, taking us on this green journey. Thank you to our sponsor LKI Consulting and to It's Water and Coma Media for our music. And I'm looking forward to chatting with everybody next month.